Hi, everybody. I'm pleased to be here today as part of this conference to present to you. I'm sorry I couldn't be there in India with you in person. I hope to someday be able to do that, but for now, my obligations here at UCLA are just too big to allow me to travel for an extended period this quarter. Today, I'm excited to talk to you about some work we've been doing on evaluation of ground failure potential due to liquefaction or cyclic softening due to vertically propagating shear waves combined with soil structure interaction from shallow foundations. This is work I've been doing with my colleagues Jason Bunker, who got his PhD with us a few years ago, now works for Shannon Wilson, and Professor Jonathan Stewart at UCLA. So the motivation for our work is that traditional liquefaction, triggering, and cyclic softening procedures are really corresponding to level ground free field conditions. So I'm showing those conditions here. Turn on my laser pointer. So this is showing a free field level ground site with vertically propagating shear waves. I'll turn off my camera here so you can see the citation. So we assume that the waves are propagating up. There's a vertical stress and a horizontal stress existing on the ground, and then there's a shear stress that acts on horizontal and vertical planes that carries those shear waves to the surface, where there's a surface acceleration time series denoted by A here as a function of time. Here's a photo from a field in the Imperial Valley down where I grew up, and it's showing the Kornblum Road site, where this is really free field level ground, right? This is an agricultural field, very flat. You can see sand boils have come up here, so this is kind of an ideal site to look at for this free field condition. And based on this free field condition, we've defined a cyclic stress ratio. So CSR is this R sub E factor multiplied by the acceleration in units of G times sigma V naught over sigma V naught prime times R sub D. So this RE is a function that allows us to take a broadband time series and represent it using an equivalent number of harmonic or uniform cycles at some amplitude. Typically, R sub E is taken as 0.65. This A max over G times sigma V naught term times R sub D is basically the maximum shear stress that exists on horizontal and vertical planes. So we can rearrange this equation to be simpler and just say R sub E times tau max. And then we divide that tau max by sigma V naught prime. So we divide by the initial vertical effective stress to get the cyclic stress ratio. So one thing about this equation is that we're using a single component of stress to entirely define the demand. We can think of this in terms of stress tensors. So we have an initial stress condition composed of a vertical stress acting on the ground surface. Here we go. There's the vertical stress acting at some depth, and then the horizontal stress would be the same in both directions for free field level ground conditions. And then we add to it some change in stress during the earthquake. And vertically propagating shear waves only cause changes in the shear stress acting on, for one-dimensional wave, acting on one plane. So there's taus on this off diagonal, everything else is zero. We can add that together, and this gives us the actual shear condition or the stress condition under the combined effects of the initial static loading and the cyclic loading. So just because we only have tau here, the delta sigma is only a single component of stress that allows us to use that component to define demand. Things get more complicated when we have structures. So here's building B1 that in Adapazari that tilted and had a bearing capacity failure due to the Kocheli earthquake. This is a picture by Jonathan Bray, and you can see the peer report down here documenting that. All right, in this case, we have a more complicated initial stress condition because there are initial shear stresses. The vertical and horizontal stresses may be different due to the weight of the structure resting on a shallow foundation here. So our initial stress condition is more complicated. It's in this case a fully populated Cauchy stress tensor, although some of these may be zero depending on the problem and the location beneath the footing. Then when the vertically propagating shear wave comes up, it only induces shear stress on horizontal and vertical planes, but the structure vibrates and has its own dynamic response and induces extra components of stress on the soil. So this stress tensor is also fully populated, And then we end up with this much more complicated condition and a more complicated Cauchy stress tensor at a point. And of course, that stress tensor will vary spatially beneath the structure. In this case, we don't have a single stress component in the delta sigma tensor. And so it's not clear exactly how we are going to define our cyclic stress ratio. We can't just take shear stress on horizontal and vertical planes because the stress condition is more complicated now. So I'll talk a little bit about modes of deformation and failure, and a little bit about some of the literature on predicting settlement of structures on liquefiable ground that may fail. All right, so some of the modes of deformation are flow of water, volumetric strain that can cause structural settlement. That's one that is typically accounted for. A lot of the time we assume that a structure will settle based on a prediction of volumetric strain in the sand due to liquefaction. Of course, there are other mechanisms of potential failure, like rotational failure. This is a shear mode, punching settlement, and this is from Dashty and Bray, 2013. You can get this rotational mechanism, compression and tension. Of course, there are other mechanisms too. You can get ejecta of sand. So there's volumetric strain, deviatoric strain, and ejecta. Those are the primary modes by which you might get structural settlement. And so there has been quite a bit of work in this area to sort of integrate numerical modeling with either centrifuge modeling and or field observations of settlement of structures to try and develop equations for predicting the settlement of a structure due to liquefaction. So this is some work from Bray and Macedo. Shade Dashty at University of Colorado has done work on this too. I'll show one of her slides next. What they've done is run these 2D finite element simulations and come up with a regression equation to those results to predict the amount of deviatoric settlement, right? So these are undrained simulations, and the deviatoric settlement is just due to rearrangement of the soil elements, not to volumetric strain. And this depends on a number of things, including foundation properties, loading conditions, and so forth, thickness of the layer, things like that. Then they add in components for ejecta-induced settlement and volumetric strain on top of that and get a total amount of settlement as a result. So it's an empirical equation calibrated to numerical models and centrifuge models. Shade Dashty and her colleagues have done this in 3 dimensions. So this is a model showing a soil profile and then a 3-dimensional structure here. They've run a large number of numerical models using high-performance computing clusters and come up with equations to represent the numerical value of settlement. So these are regressions that give you the amount of settlement predicted by the numerical model. And they're fairly complicated. They're using cumulative absolute velocity, which the Macedo and Bray equation also uses. There are benefits of using CAV because it integrates demand over time. So a long duration event will have a higher CAV for a given shaking intensity than a shorter duration event, which we know has an impact on liquefaction and structural settlement. And what they've done then is adjusted their equation for field case history observations. So they gathered together a whole bunch of literature on field settlements and provided adjustment factors because numerical models don't fully capture everything that happens in the field. So it's always good to do that sort of correction. So that brings me to the motivation for the work that we're doing, which is a little different from these sort of settlement predictions. So the motivation for our work is that traditional procedures for evaluating liquefaction or cyclic softening assume one-dimensional wave propagation. Past case histories have exhibited ground failure beneath structures, but not in the free field. That's something I forgot to mention when I showed that building that tipped in Adapazari. There were silt boils and signs of ground failure beneath that structure and in the vicinity of the structure. But if you went away from the structure to the free field, there were no signs of ground failure. So that's evidence that soil structure interaction played a role in that failure, and that if you just did a free field analysis, you would underpredict the potential for ground failure. So these existing methods for predicting settlement are very useful, but I would point out that they are constrained, they've been constrained by field observations or centrifuge observations, which is good. They're tied to some measurements. But they're limited to the range of numerical and field validation. If you have a case, a building, or loading condition that doesn't match the conditions that were in those numerical models, you can't really use those equations with much confidence. And they also give you a settlement, so it's not predicting whether or not soil will fail at a point, but rather how much settlement is a building going to have, which is very useful. Our method is focused on whether failure is going to happen at a point, so it's more like a triggering analysis or a cyclic softening analysis that we do for a one-dimensional soil column. So we need a method that defines CSR for the complex stress paths that exist beneath foundations. We have it for one-dimensional propagating shear waves. We don't really have that yet for the complicated loading conditions, and that's what I'll present today. So our methodology is going to focus on two aspects. One is demand, right? So we're going to assume vertically propagating shear waves in the free field, but then those combine with SSI-induced stresses from a shallow foundation. And what we'll do is limit ourselves to plane strain condition, although the concepts are general enough that you could substitute these for three-dimensional equations for the stress field beneath a loaded area. So here's the free field stresses that we have, right? So these are corresponding to that vertically propagating shear wave. You get some initial, so the sigma ZZ naught comma FF is the initial vertical stress in the free field. It's just the integral of unit weight with depth. Sigma XX naught free field is equal to sigma YY naught free field, right? So we're assuming free field horizontal stresses, and we just introduce a K naught parameter there. And we do this on effective stresses. So this is now the vertical effective stress times K naught, and then we add back in the pore pressure to get the horizontal total stress. So our stress equations are total stresses. We're assuming undrained loading conditions. It's hard to predict pore pressures due to these stress increments, so we're going to do a total stress analysis here. And then we get shear stress on horizontal and vertical planes, and we will introduce the traditional R sub D here. So it's surface acceleration times the mass density and depth times R sub D, right? So we can get that stress condition. Okay, then we're going to make some assumptions about the footing. So we'll assume it's a flexible strip footing, so we can model it just as a pressure distribution acting on the surface. That pressure distribution will account for vertical load, shear, base shear acting on the bottom of the footing, and then moment, right? So we'll use it'll be kind of a trapezoidal incline distribution when you sum up these three components. We're also going to assume that the soil is an isotropic elastic half space. Now, I understand that we're solving a ground failure problem. Soil is not elastic. That's exactly what we're trying to figure out, is whether the ground is going to fail. It's almost certain that the elastic assumption is wrong. But I would just point out that when we do vertical propagating shear wave free field liquefaction, we use the ground motion that would exist in the absence of liquefaction. And so in a way, we're using an elastic demand, or at least an equivalent linear kind of demand. And we're not actually trying to account for all the nonlinearity when we define the demand. So all we're doing is defining demand here using elastic equations because they're available. And I'm also going to assume that loading frequency is low enough that static elastic solutions are reasonably accurate. Okay, in reality, a vibrating structure will propagate waves through the soil. It's a dynamic stress condition. That's very complicated. You have to account for amplitude and phase and things like that. We're not going to do that. We're going to assume it's static. And our preliminary analyses show that for points that are close enough to the footing, where the footing is really affecting stress, that tends to be a pretty good assumption for typical earthquake frequencies. So there's not a lot of error involved there because our dimensionless frequencies are low enough that we can do it statically. So given all of those assumptions, we can define soil structure interaction stresses. And these are just from elastic solutions. You can find these in a lot of places. Poulos and Davis famously put these all together into a single reference and synthesized a bunch of literature. So you could find these there. There are multiple components here. So there's the component of stress from the vertical load, from the shear, the base shear, and then from the moment. And this is vertical stresses at a point. We have horizontal stresses at a point in the XX direction, and then we have shear stresses at a point, the XZ direction. And then the sigma YY direction, we use elastic solutions, and it's a function of Poisson's ratio, that stress in the out of plane direction. So we end up with that fully populated stress tensor shown here, and we can then compute principal stresses by simply taking the eigenvalues of the Cauchy stress tensor, right, at any particular time and at any point. So we get sigma 1, 2, and 3. Then in order to define a CSR quantity, what we do is use deviatoric, we use invariance, right? So here's the deviatoric stress invariant, square root of a half times the sum of the square of the difference in principal stresses. So you have to compute these principal stresses first, then compute Q. For a triaxial compression stress path, this just comes out to be sigma 1 minus sigma 3. But for a more complicated stress path, it's hard to know what this is going to be ahead of time. You just have to compute it. We can also get mean effective stress. So P naught prime is just the average of the three principal effective stresses, or it's 1/3 of the trace of the effective stress tensor. And then here's the classical definition of the cyclic stress ratio. So what we would like to do is now define CSR in terms of Q and P naught, because it would be fully general. We could then use it for any complicated stress path. And so we have to replace the tau and the sigma V naught prime, because these are individual stress components. They may not correspond very well to a more complicated stress path. So the way that we do that is to derive Q and P naught for free field level ground conditions, so that our CSR definition is exactly the same as the classical definition of CSR in the free field for vertically propagating shear waves. So here's our definition of CSR. These are our stress tensors for this loading condition. We can compute the invariance, right? So P naught prime is simply sigma V naught prime times 1 plus 2 K naught over 3. Q naught is just the difference between the vertical and horizontal initial principal stresses, right? This is the initial deviatoric stress invariant. And then if you solve for the eigenvalues of this stress tensor over here on the right, you can show that Q, the deviatoric stress invariant, is equal to the simple quantity here in terms of tau. So what we need to do now is solve for tau, plug it in here, solve for sigma V naught prime, plug it in here, and we will have our expression shown here for a invariant-based definition of cyclic stress ratio that is equivalent to the traditional CSR for free field wave propagation. So here's that equation, and I've added a sign here because it's possible that Q would be less than Q naught, and that would correspond to unloading instead of reverse loading. So we add this sign convention here to account for that, and CSRQ can actually be negative in that case. Now we have to move on to resistance, right? We've got the demand part. CSRQ is all that we need to compute for any kind of complicated stress path, but how do we adjust the resistance? Because our resistance quantities also assume vertically propagating shear waves and direct simple shear stress path. So here's the classical equations for liquefaction resistance, right? Cyclic resistance ratio for liquefaction triggering. CRR ref is a function of relative density. Then we use a magnitude scaling factor, which is basically accounting for duration or number of loading cycles. And then we have a K sigma to account for the influence of vertical effective stress or confining pressure on the cyclic resistance. Soil becomes more contractive as sigma V prime goes up, so K sigma will reduce the resistance. And then K alpha accounts for any static shear stress effects. Okay, then we have CRR for cyclic softening of clay. In that case, we can use a tau cyclic over SU framework like Boulanger and Idris, 2006. And so and then there's a correction for two-dimensional loading. Often this is taken as being 0.9. And so we have the same magnitude scaling factor and K alpha factors. K sigma is typically absent here because we assume that the influence of effective stress is the same on the monotonic undrained strength and on the cyclic undrained strength. When we go to a fully general analysis for any stress path, not just simple shear, there are a few adjustments we have to make. So first, the magnitude scaling factor may be a little different because the number of loading cycles from a structure is generally different than the number of loading cycles in the free field. K sigma is basically the same. We just substitute P naught prime instead of sigma V prime to make it general. And then K alpha is divided into a capacity and a demand term, and I'll talk about that in a minute. And then we have a path correction, K theta, to account for the fact that direct simple shear stress paths have different shear strengths than other stress paths. So here's the liquefaction one. The CRR ref is the same as this one. And then similarly here, the only thing we're doing is adding a K sigma, adjusting K alpha C. Maybe the magnitude scaling factor needs adjustment too. So here's how we do our path correction. We use the load angle, which is defined here on the top. This theta is basically an angle that will take a stress tensor and figure out what stress path you have. So this could be triaxial compression, direct simple shear, triaxial extension, or really anything in between. And then here's a plot for anisotropic strength depending on the stress path. So if you set the C parameter to 1, the strength is the same regardless of path. If you set it to something other than 1, you can get like a higher strength, for example, in triaxial compression than in simple shear. And we're using direct simple shear as our reference. So all of the points here are 1, which means that when you specify a monotonic undrained strength, it should correspond to a direct simple shear stress path, and then you can adjust this C to account for the difference between that and different stress paths. So we take this ds, this deviatoric component of the stress tensor here, and then we compute a K theta based on the theta that we compute from the load angle up here. All right, K alpha is an interesting thing, right? K alpha actually accounts for 2 different effects. First of all, static shear stress. When you impose it on soil, you bring the soil closer to failure statically. And so there's less capacity for that soil to absorb cyclic loading because it's already closer to failure prior to cyclic loading. This is important because our methodology inherently accounts for initial shear stresses in the formulation. CSRQ that we've defined will be different if you have static shear stress than if you don't have static shear stress. So it's inherently embedded in our method. It's not inherently embedded into traditional methods with vertically propagating shear waves. Then there's a second effect, and it's that static shear stress alters soil fabric. It changes the way the particles interact with each other, and that changes cyclic shear strength. So that's a capacity effect. The way we've broken this down is to say that K alpha is the product of these 2 factors. We have a demand factor and a capacity factor. The demand factor that comes out of our analysis is given by this equation right here. It's CSRQ with alpha equals 0 divided by CSRQ with some alpha that's not 0. And so if you have a cyclic stress right here, cyclic shear stress on horizontal and vertical planes, and you have a static shear stress, you can define this K alpha D for direct simple shear stress path. Then we define K alpha C based on the ratio of those capacities. And we went through and looked at some of the data that was used for fine-grained soils, and we revised those calculations to give us a K alpha C parameter. And when you do these corrections, you see that the capacity effect initially increases. So soil gets a little bit stronger as alpha increases, but then it comes down, and eventually when you go to a static failure condition, there's no cyclic strength anymore. It's way down there. So we've come up with this methodology, and then we conducted a set of centrifuge models. And so this is from a paper there's another paper in Earthquake Spectra here that we authored that describes the entire testing program, and all of our data is also published. So if you're interested in going to gather these data and use them, you can find them on DesignSafe and through our data paper. Feel free to reach out to me if you'd like to have that. We tested 3 structures. So there's a simple single degree of freedom oscillator here, and then 2 portal frame structures with different natural periods. Then we had kind of a free field array over here. The first model had a single layer of clay. The second model had 3 layers of clay with little sand layers in between. And I'll talk only about this top model here for this presentation. So first we did some cyclic strength testing of our soils, and we came up with a relationship for the tau cyclic over SU versus number of cycles. We used a bentonite freshwater blend and a kaolinite freshwater blend, and the kaolinite one is what we used in the second model. The bentonite one was in the first model. So this is the curve that we'll be talking about today. Then we shook the base of the model with a bunch of input motions that are scaled versions of real earthquake ground motions. So this is these are different scaled versions of a motion from Chi-Chi, Taiwan, the TCU 078 record. It's one of the horizontal components. I forget which one. And then we also shook the model with this Port Island ground motion from Kobe at a depth of 83 meters. So it's the downhole record from that array. And then we did the same for the second model as well. This is an example response for one of those ground motions. So here's the acceleration at the base of the model. You can see that the ground motion was amplified through the soil column, so the shaking intensity in the far field was higher. And then here's the shaking at the top of structure 1. So structure 1 was our single degree of freedom oscillator. You can see it de-amplified the motion because the natural period was pretty long. We were on the tail of the response spectrum of this structure, and so the shaking intensity was not that high. Then we can use the sensors to calculate base shear. We also got rotation, so you can see that this one was rotating during shaking, rotated by a little bit more than 2 degrees during shaking, and we set this to 0 at the beginning of the record, even though there might have been some residual rotation from previous motions. Then you can see it's settled by about 10 centimeters, and these are in prototype unit. The settlement here is prototype units. So what we did now was used our methodology to compute the initial stresses. Here's the initial mean stress and then the initial deviatoric stress. You can see that the structure does alter these things, right? The mean stress tends to be higher beneath the structure, deviatoric stress is higher, and then as you move away, you get more to a free field condition. And then here we're plotting those same, we're plotting the deviatoric stress invariant at the time that the peak far field surface acceleration happened. So you can see that there's some rotation. The structure is imposing demands here and creating increased Q right beneath this corner of the footing. We use the measured base shear moment and vertical load to use our stress equations here and compute these fields. And then you can see over here is tau Q over SU, where tau Q is basically like a dynamic component of CSRQ. So if you take CSRQ and multiply it by P naught prime, or the equivalent sigma V naught prime, you can get the shear stress equivalent. So this is like a shear stress that's equivalent to a direct simple shear stress path, but it accounts for the complexity of the stress path, and we've normalized that by SU. So you can see we're going over 1 here. We're getting significant shear stress demands on the soil. Here's the definition of tau Q right there, DSS equivalent shear stress. We're plotting it versus time here beneath the structure, so that's on the top, and then in the free field. And you can see these are significantly different, right? Beneath the structure, there's much more shear stress happening. In the free field, there's not a whole lot happening. And the equivalent number of loading cycles is different. So we got about 80 loading cycles beneath the structure at a depth of B over 2, where B is the footing width, the footing half width. And in the free field at the same depth, we only get 42 cycles. So the fact that the structure is ringing around and imposing additional cycles changes the number of cycles and therefore the magnitude scaling factor. So then we can compute CSRQM, which is the CSRQ value adjusted for the number of loading cycles that we have. And this could be directly compared with the capacity. And so here's the factor of safety, right? If we take that CSRQM and divide by CRR, we would get this factor of safety, and you can see that it's going below 1 quite a bit, right beneath the corners of the footing, and maybe a little bit over here in the free field, but there's not a whole lot of factors of safety less than 1 over in the free field. It's predominantly below the footing. And then if we were to plot these factors of safety averaged vertically at the corner of the footing, beneath the, throughout the thickness of the clay layer, we could plot that versus a dimensionless settlement here. So this is S over 2B, where 2B is the full width of the footing. So this is like how much did the structure settle relative to its base width. What we see is that as the factor of safety goes below 1, we start getting settlement, right? We start seeing significant settlements. It doesn't have a perfect relationship here. It just kind of goes to high settlements once we get down below 0.75. But you can clearly see there is a trend, and settlements are not that big if the factor of safety is higher than 1. Just for fun, we also did a free field analysis. So instead of accounting for the structural demands, we just looked at the free field ground shaking. And what we see is that the agreement here is not very good. All right, we see significant factors of safety higher than 1 in the range of 1 and 2 that are associated with big settlements, right? Like 2%, 2.5% of the footing width kind of settlements. These are big settlements that could be interpreted as bearing capacity failures, even though the free field factor of safety is higher than 1. That's consistent with what happened in Adapazari. That building tipped over and had a bearing capacity failure. There was no free field ground failure in that case. So our conclusions, we developed an invariant-based procedure. So we took complicated stress fields beneath footings, computed the mean stress and the deviatoric stress invariant, so 2 invariants, and we reframed the cyclic stress ratio in terms of those invariants instead to allow us to use those invariants to compute an equivalent CSR quantity that can be used for ground failure analysis. So it accounts for the complex stress paths arising from shallow foundation SSI. In our case, we did this for plane strain conditions. Our centrifuge models were essentially plane strain. The method itself is fully extensible, so you could extend it to 3-dimensional loading conditions. When we applied this to centrifuge models, we find that the factor of safety averaged vertically beneath the corner of the footing was lower than in the free field, and it related better to observed foundation deformation. We would underpredict foundation settlement if we used a free field analysis in this case, which is the traditional method that we do in engineering practice. There are limitations of our method. We're aware this is not a perfect method. So I'll just go over a few of those limitations here to end. So first, the stresses are for flexible foundations. Real foundations are not fully flexible or fully rigid, right? They're going to have some finite flexibility. The stress field beneath the footings are going to vary, and they'll differ from what we have here. As you move away from the corners of the footing, especially due to St. Venant's principle, those stress fields become closer to the same. So the difference between flexible and rigid foundations are very high right at the corners of the footing. As you move away from those corners, they become more uniform. So it depends kind of on where you're looking. Is the soil going to fail right at the corner, or do you have a layer above it and the soil's down below? Maybe the flexible foundation assumption is better for that condition than if the footing rests directly on top of the soil that may fail. We use static stress solutions, but the real problem is dynamic. SSI-induced wave propagation might be important at high frequencies. So we used ground motions that are from pretty active tectonic regions. Ground motions in stable continental regions tend to have higher frequency content. That might be an issue. Also, if you're looking at a large distance away from the footing, there's more opportunity for that wave field to form and be out of phase with the free field ground motion propagation. This is a problem that in principle can be solved. There are dynamic solutions for things like vertical point loads, horizontal point loads, but they would have to be developed for these full foundations, and phase and amplitude would have to be considered. We use linear elastic solutions, even though the soil is nonlinear and inelastic. We're actually trying to predict whether it will fail, so obviously it's a nonlinear problem. We would just argue that our approach is analogous to existing level ground assessments where we use demands that would exist in the absence of liquefaction. So maybe elastic solutions are not all that bad. For the most part, they're independent of modulus. They just are equilibrium considerations. In our case, we used SSI demands that were measured. We had accelerometers on the structure. We knew its mass. We could compute base moment, base shear. We knew the vertical loads. In a real problem, those would have to be estimated. And so this is where you would need to work with a structural engineer, right? Maybe you could take the results of a nonlinear structural analysis to get the base shear and moment to estimate ground failure. Now, that would require iteration and communication. Geotechs often do their work at different times than structural engineers in the context of a project. So this is a difficult thing too that I think can be overcome. So to end, I'd just like to acknowledge that the National Science Foundation funded this work. Any opinions are ours. They're not necessarily views of the National Science Foundation. And then we had a lot of help from people at the UC Davis Center for Geotechnical Modeling. So the CGM staff, others at UC Davis really helped us a lot to get this project executed on their large centrifuge. And then we also would like to thank Mandro Islami, another former student here, for the contributions during the construction and testing the model. He did a lot of the material testing on the soils that we presented too. And I will end it there. Thank you.